Asteroid Bennu is a lump of rock and organic material, the early building blocks of the solar system and Earth. The raw ingredients of Bennu and our solar system originated in a stellar nursery billions of years ago. In a colossal explosion of a supernova, clumps of dust not much larger than a grain of wheat were flash-heated into droplets of molten rock called chondrules. Chondrules were destined to become the building blocks of the solar system. They grew into the first asteroids and into planets. Asteroids are rubble piles of rock, metal, ice, and organics. One large asteroid, a protoplanet, was the parent body of asteroid Bennu. Then 1 billion years ago, a collision shattered Bennu's parent. Some of the debris loosely coalesced into a new, smaller body which became Bennu. Bennu had a dull, non-reflective surface, causing it to slowly migrate toward our Sun. Through millions of years, Bennu's orbit gradually tightened. Close encounters with the Earth and Venus followed. Their gravitational pull repeatedly stretched, tore off loose material, and reformed Bennu. Bennu is nearly spherical and is quite accessible thanks to its relatively Earth-like orbit. Bennu completes one lap around our Sun every 14 months, or 1.2 years, and comes into Earth's neighborhood every 6 years. The orbit is inclined by just 6 degrees compared to that of Earth. Bennu has a very dark black surface, the color of coal, that scientists think indicates high concentrations of carbon and hopefully a form of organic materials that could date back to the origins of the solar system, some 4.5 billion years ago. Bennu is a time capsule that could help explain how life began on Earth. So scientists hope to bring back a pristine sample of the early solar system and determine if asteroids like Bennu delivered organic material and water to the surface of the Earth, creating habitability and the origins of life on Earth. Bennu is shaped like a ball with a fat middle. Scientists believe the bulge at the equator is made of loose rubble or gravel and is ideal for collecting a sample. Bennu is nearly 1,650 feet in diameter, taller than the Empire State Building. And it rotates every 4.3 hours, so a day on Bennu is just over 4 hours. It rotates slowly enough to allow contact. Bennu was discovered in 1999 and was known as 1999 RQ-36. 14 years later, it was renamed Bennu, after the heron of Egyptian mythology Bennu. It is the best understood near-Earth asteroid that has never been visited by a spacecraft. Bennu is classified as a potentially hazardous asteroid, and there's a slight chance it could slam into the Earth. In 2135, the asteroid will make its closest brush with us, swinging by Earth at about 220,000 miles away. That's closer than the Moon, which orbits about 240,000 miles from Earth. But chances of a collision happening are just 0.1%. A trip to Bennu will allow researchers to fine-tune their understanding of Bennu's orbit and any threat it may pose to Earth. Near-Earth asteroids like Bennu do pose a potential danger to our planet, so it's important to predict their orbits with great accuracy. It is difficult, however, to make these predictions over long periods of time. One force acting on the orbits of asteroids comes from the solar energy that asteroids absorb, and then radiate away as heat, in a phenomenon known as the Yarkovsky effect. When sunlight strikes a rotating asteroid, the day side heats up. As the asteroid turns, the night side cools and releases the energy as heat, acting kind of like a mini thruster that can change the asteroid's direction over time. If you want to be able to predict where an object like Bennu is going to be in the future, you have to account for this phenomenon. So why travel to an asteroid? Over the last 100 years, human population on the Earth has exploded from about 1.5 billion to more than 7 billion people, driving an ever-increasing demand for resources. To satisfy civilization's appetite, communities have expanded recycling efforts, while mine operators must explore forbidding frontiers to seek out new deposits, opening up mines deep underground or even at the bottom of the ocean. Asteroids could one day be a vast new source of scarce material. Asteroids are lumps of metals, rock, dust, and sometimes laced with ices and tar, which are the cosmic leftovers of the solar system's formation. There are hundreds of thousands of them, ranging in size from a few yards to hundreds of miles across. Some asteroids have high abundances of water bound up as hydrated clay minerals. Currently, these asteroids have little economic value since water is so abundant on Earth, but they will be extremely important if we decide we want to expand the human presence throughout the solar system. Their water content could be broken apart into hydrogen and oxygen, which could be used as rocket fuel. This could enable fuel depots out there where we are mining asteroids. Some asteroids also have a lot of organic carbon, phosphorus, and other key elements for fertilizer for astronauts to grow food. Other asteroids have very little water, but contain a significant amount of iron, nickel, and cobalt, as well as gold, platinum, and rhodium. It currently, however, costs hundreds of millions, if not billions of dollars to build and launch a space mission. So innovations that would make these costs fall dramatically are needed before it is profitable to mine asteroids for the value of their metals alone. Because of our lack of experience with mapping and analyzing the resources in asteroids, and to extract material from them, missions like OSIRIS-REx may help us to gain this kind of critical information. Launched by NASA on September 8, 2016, and rendezvousing with Bennu in August of 2018, OSIRIS-REx will study the asteroid in detail, retrieve a sample, and return it to Earth. The study will give researchers insight into Bennu's orbit and composition, as well as develop important technologies for asteroid exploration and possible mining of them. Since being launched by NASA in September 2016, OSIRIS-REx has entered a deep space orbit around our Sun. It will travel along this orbit for a little over a year. In September 2017, 1 year after launch, OSIRIS-REx, at its farthest distance from the Sun, will perform a deep space maneuver to aim for Earth to make a gravity assist flyby of Earth. It will use Earth's orbital energy to slingshot the spacecraft farther into space and enabling it to reach Bennu. In August 2018, OSIRIS-REx will complete the 2 million kilometer journey to Bennu and make its way into a 1 kilometer polar orbit. The spacecraft will need to slow down to an approach velocity of just 0.45 miles per hour. Beginning October 2018, OSIRIS-REx will survey the asteroid for about a year, mapping it in total, identifying strange or unique geological features. It will use its instruments to create a 3D map of the asteroid's surface. It will create a high-resolution global dataset containing color images, altimeter data, and spectrographic data, and select an ideal spot to retrieve a sample. About 2 years after surveying the asteroid, in July 2020, the spacecraft will begin to position itself in preparation for an acquisition of a sample from the surface of the asteroid. The spacecraft won't be hitting Bennu, but rather make a maneuver that has been described as a safe, smooth, slow high five. This touch-and-go maneuvering will last about 2 months and will be executed at about 0.22 miles per hour. At least 2 ounces or 60 grams of asteroid material will be collected. Then the spacecraft will spring back out into a safe orbital distance. March 2021 is the month the window for departing Bennu opens up. OSIRIS-REx will execute a main engine burn that helps put the spacecraft on a path towards Earth, with the goal of making it back to Earth by around September 2023. During September 2023, OSIRIS-REx will jettison the capsule containing the asteroid sample, about 4 hours away from atmospheric re-entry. The sample will dive back toward Earth and land in the Utah desert for NASA to retrieve and bring back to the Johnson Space Center in Houston. OSIRIS-REx itself will perform a deflection maneuver that shoots it back into a stationary orbit around our Sun, ending its 7-year mission to Bennu. Although developed for science, the instruments on OSIRIS-REx are similar to those necessary for an asteroid mining mission. The success of the OSIRIS-REx mission to Bennu will show us that we can, in the future, go to an asteroid, get material, and bring it back to Earth.